All right. Now 10.2, let's have a look at this. In a different photoelectric experiment, blue light obtained from a light bulb is shone onto a metal plate and electrons are released. Good. The wavelength of the blue light is 470 times 10 to the minus 9. That could also be 470 nanometers. So that's the wavelength of the light. We've got to do some conversions. You remember C is equal to F lambda, speed of light, the frequency of the light, the wavelength of the light. And the bulb is rated at 60 milliwatts. Again, this tells me something. Remember that watts tells me something about the amount of energy per second that I'm going to get out of this. However, here's an interesting thing. The bulb is only 5% efficient, so only 5 parts in every 100 of that is going to be useful to me. So here is a little twist in the tail that you have to take into account. Calculate the number of photons that will be incident on the metal plate per second, assuming that all the light from the bulb is incident on the metal plate. Well, let's see what we can do with this. Okay, energy radiated per second. The energy per second by this blue light bulb. Okay, that is going to be equal to, now, we take into account its efficiency, 5/100ths. And then we take into account the wattage or the power output if this thing is operating optimally, however, optimally, but at a low, fairly low, as optimally means it's putting out as much light as it can. And that's the rating. 60 times 10 to the minus 3, which is milliwatts, but we see it is not all that efficient, so we have to take this into account, and that is going to be 5 times 60 is 300, and times 10 to the minus 5, so that is going to be 3,0 times 10 to the minus 3 joules. Okay? 3 times 10 to the minus 3 joules. That is the amount of energy that it delivers per second. Okay, now, the energy of the photon is going to be given by HF or HC over lambda. And I'm going to use this form of the equation. Why? Because I've got some wavelength information that I think I'm going to be able to use. So the energy of the photon that is emitted is going to be 6,63 times 10 to the minus 34, an extremely small number, Planck's constant. The speed of light is 3 times 10 to the power 8 meters per second, and the wavelength, we were told, is 470 times 10 to the minus 9 meters. And when I work that out, you've got a calculator, is 4,23 times 10 to the minus 19 joules, and that 10 to the minus 19 is the kind of expected order of magnitude for the energy of a photon. So therefore, let me carry on working over here. The total number of photons per second. Now, that takes us back to this, is going to be 3 times 10 to the minus 3, which is the effective energy that we get from the light bulb, divided by the amount of energy required to release one photon. So if I divide the energy per photon into the total amount of energy that is available to me, so this is going to be joules, and this is going to be 4,23 times 10 to the minus 19. And what are these units? This is 4. What does that mean? This is joules per photon. Joules per photon. You'll see that per photon thing goes up to the top. The joules cancel out effectively, and then we're going to get 3 over 4.3, so it's going to be something just less than 3/4, so it's 7,09 times 10 to the power 15 photons. Now, this just gives you some indication. Look at this, 10 to the power 15, that's 1 with 15 noughts. Billions and billions of things from this weak little light bulb shining onto a piece of metal. But look at, nevertheless, how many photons are released. Because we are dealing with extremely small things here, and we're dealing with things that have very low, very small bits of individual energy. But, of course, when you get things in that sort of number, then you really are looking at fairly well, you're looking at something that can have an effect, even if it's a fairly soft blue light and so on. You've got all these photons, and so if each one of those releases an electron from a surface, then you're going to get some reasonably effective current. Remembering that an electron, of course, has also got a very low charge, which is 1,6 times 10 to the minus 19 of a coulomb. But we've got low individual charges, but many, many, many of the things that can knock electrons out. And so it all sort of squares out, and it gives us the kinds of currents and so on that we can measure in our world. Okay,